share my screen, please?
Yes, Professor Manuel Coimbra will tell you that, okay?
Okay, thank you.
So let me connect here. Podem vocês ligar depois também no YouTube só para ver se está. Já estás lá, já estás lá. Okay. So we are okay. Hello, good morning, everyone. Good morning. Welcome to the third day and last day of the 7th PYCHeM. Hope you are enjoying the Congress. The last days were very fruitful and very good with high scientific quality oral communications. And today is not different. We will have a full day full of very interesting communications, and we will begin the first session of today's work with Dr. Manuel Coimbra as the chair session. So I'll pass on to you the word, Professor Manuel. Thank you so much.
Hello, good morning, everybody. So let's start our morning session with a talk by Dr. Christine Morin from the Human Nutrition Unit, Diet, Plant Food, Bioactives and Vascular Health, NutriVasc in France. Dr. Christine Morin studied biochemistry and cellular biology, and she's PhD, and she received the PhD at Blaise Pascal University in Clermont-Ferrand in France. So she's a full researcher director at INRA-E, that is a very famous institute in France, and now the biggest one because it joins agriculture and environment sciences. And she is working at that unit of human nutrition at Clermont-Ferrand, where she leads a group focusing on plant food bioactives and vascular health. So she has a long and lasting experience in the field of nutrition and health, and focusing research on the role of dietary polyphenols in the prevention of cardiovascular diseases. And the approach is an integrated approach that combines the clinical and the mechanistic studies. And just to finish her presentation, let me just say that she is the chief editor of Food and Function Journal that the majority of us know. So thank you very much, Dr. Christine Morin. So the virtual floor is yours.
Okay. I think it is okay with the presentation now. So first of all, thank you very much, Manuel, for this kind introduction, and good morning, everyone. So I am Christine Morin, nutritionist at INRA-E. And to start, I'd like to thank the Portuguese Society of Chemistry for inviting me to give a lecture at this 7th Portuguese Young Chemist meeting. I would have loved to be on place to give this talk in order to discover the wonderful city of Bragança, but unfortunately, due to the COVID pandemic, we are only meeting online for this time. In any case, it's a great pleasure for me to present to a large audience of chemists some results of our research that were carried out over these last years in my lab and elsewhere, and that illustrate the key role played by phytochemicals in the vascular protective effects of plant foods. It is well established that dietary patterns influence a range of cardiometabolic risk factors, and also that dietary patterns rich in plant foods are both the most sustainable and the more protective for our health, with a high level of evidence regarding especially cardiometabolic health. The high nutritional value of plant foods when minimally processed include fruits, nuts, seeds, vegetables, legumes, whole grains, and vegetal oils. And their interest lies in their low glycemic load and low salt content, together with the high content in fibers, vitamin, minerals, and also in the presence of a variety of bioactive compounds that are exclusively found in plant foods. Based on their content and distribution in foods, the most important families of plant food bioactives in our diet include polyphenols, carotenoids, plant sterols, and glucosinolates. Some of these families, like polyphenols or carotenoids, are quite ubiquitous in foods, whereas others are more specific to some category of foods, like glucosinolates in cruciferous or plant sterols in oleaginous products. According to some structural features, most of the categories of plant food bioactives are divided in different classes and sometimes also subclasses. This is especially the case for polyphenols, divided into flavonoids, phenolic acids, and lignans, curcuminoids, and stilbenes for the less abundant ones. Depending on dietary habits and food preference, the respective levels of intake of these bioactive compounds is quite variable between individuals, but in total, their mean intake is over 1 gram per day. Based on their content and distribution in foods, the most important family of plant food bioactives in our diets Voilà. Based on their chemical structure, the most abundant phytochemicals in our diet, as I told previously, are plant sterol, carotenoids, polyphenols, and glucosinolates. And considering the wide range of their biological activities that have been demonstrated in animals models or in vitro, together with increasing evidence from large prospective cohort studies and the growing number of results from clinical trials that report positive effects on some intermediate biomarkers of health, including blood lipid profiles, glucose metabolism, and insulin sensitivity, and vasodilation and blood pressure. These plant food bioactives appears as interesting food constituent for improving health and preventing age-related chronic disease and associated disorders. And this interest for phytochemicals for human health has already been underlined several years ago by nutritionists, noting that if plant food bioactives are not, as classical micronutrients, are not essential for growth and development, they are essential to maintain body function and health through the adult and later phases of life. And to this end, they were qualified as lifespan essential food constituents. In the remaining of my talk, I will focus my purpose on polyphenols, which are the most abundant phytochemicals in the diet. As I said previously, depending on their chemical structure, polyphenol can be classified in different families, the two major ones being phenolic acids and flavonoids, which represent respectively about 60 and 40% of the total polyphenol daily intakes. These two large families can themselves be divided in different subclasses, including those of hydroxybenzoic acids and hydroxycinnamic acids for the phenolic acid group, and whereas flavonoids are distributed into 6 major subclasses, some of those being quite ubiquitous, like flavonols, flavanols, or anthocyanins, whereas others are specific from some foods like flavonants in citrus or isoflavone in soy products. whatever the level of intake and the diversity of ingested polyphenols compounds is tightly linked to food preference and dietary habits. To this chemical diversity is added the fact that polyphenols are rarely present as free forms in foods. Most often, phenolic acids are present as esters, with esterification with a diversity of organic acids, whereas flavonoids are present as glucosides, glycosides, or as polymers. As a consequence, more than 500 molecules can be found in plant foods. Polyphenols can confer to their food source some organoleptic properties like color. This is especially the case for anthocyanin, responsible for the red-blue colors of berries, or for curcumin, which is responsible for the yellow color of the spice turmeric. Some flavonoids can also confer astringency, like those found in tea or wine, and others are responsible for bitterness, for example, in black cocoa or grapefruits. However, other compounds are without any odor or flavor. What is interesting for these compounds is that they are not toxic for humans when consumed at doses achievable for food from food intake. Based on their basic structure, polyphenols are reducing agents. And due to these properties, they can exert radical scavenging activities. These radical scavenging properties are largely demonstrated in vitro, but as we will see after, this direct antioxidant effect is no longer observed in vivo. When we are interested in the relationship between polyphenols and health, it is important to have a clear view of the fate of these compounds in the body after intake. And in foods, polyphenols are present, as I said previously, at high levels and mainly as glycosides, esters, and polymers. And what is important to know is that the ingested polymers are not absorbed, whereas the esterified and glycosylated forms must be hydrolyzed first by the gut microbiota prior to their absorption. And another point important is that because polyphenols are recognized by the body as xenobiotic compounds, the absorbed forms are extensively metabolized in the intestine and then after in the liver by phase 2 conjugative enzymes of the host, so that in the blood and tissue, there is no native forms, but polyphenols are present as conjugated metabolites, glucuronides, sulfites, and methylated derivatives, and as metabolites of microbial origin, and they are present both at low concentration. Due to both their low bioavailability and their extensive metabolism, polyphenols do not act in the body as direct antioxidant, except in the digestive tract, where they are present in high amount and in their native forms. However, after absorption, by acting as signal molecules, which stimulates the antioxidant defense systems of the host of the body, polyphenol can exert indirect antioxidant effect. To continue the interest of polyphenols for human health, a number of epidemiological data report an inverse association between the intake of some categories of polyphenols or of polyphenol-rich foods and the incidence of some aging-related chronic disease, including notably cardiometabolic disease, with cardiovascular disease, type 2 diabetes, and metabolic syndrome, but also neurodegenerative disease and some cancers. And these associations resulting from epidemiological data are in agreement with results from animal and clinical studies that have showed effects of polyphenols consumption to improve the anti-inflammatory and antioxidant status ability to slow down atherosclerosis development, to improve some intermediate markers of cardiometabolic risk, including improve of a blood lipid profile, improved of glucose metabolism and insulin sensitivity. And these compounds have also been shown in vivo to exhibit, to modulate angiogenesis, proliferation, or apoptosis. To exert these pleiotropic effects, polyphenols have multi-target mode of action. They have been shown to act through regulation of signaling pathways and gene expression, through modulation of enzyme activity, through interaction with some cell receptors, by exerting epigenetic regulation, or also, more recently, they have been shown to induce also change in the gut microbiota, composition and functionalities. A meta-analysis of data resulting from a dozen of available prospective cohort studies have examined the association between the levels of flavonoid intake and the risk of mortality from all causes. And the results of this meta-analysis clearly show that for the highest levels of flavonoid intakes, there is a significant reduction by about 18% of a relative risk of all-cause mortality. And other strong meta-analyses involving several hundred thousand subjects have also established for that high consumption of flavonoids reduced by 10 to 15% the incidence of cardiovascular disease and type 2 diabetes. In addition, from a recent prospective cohort studies, the strong inverse association between cardiovascular disease mortality and flavonoid intake has been shown to plateaued at intakes of about 500 milligrams of flavonoids per day. Now, let's see what we know about clinical evidence. First, most of the available human intervention studies have used polyphenols-rich foods. Only few of them have been carried out with isolated compounds. And most of the clinical trial with polyphenol-rich foods have focused of some foods of high interest for industry, including cocoa, tea, coffee, and soy. That's why for some categories of foods or fruits, we have clinical data are lacking. And the published randomized control trial have described positive effects on some biomarkers related to cardiometabolic risk, blood lipids, insulin sensitivity, endothelial function, which reflects the ability of vessels for dilation, blood pressure, and arterial stiffness. And the state of the heart indicate a high consistency for protective effects of polyphenols on vascular function. A common feature of the disease for which polyphenol intake have been reported to reduce the incidence is to be related to vascular dysfunction. Indeed, the maintenance of vascular function is crucial to prevent from a range of chronic disease, including cardiometabolic and neurodegenerative diseases. And vascular function is highly sensitive to unhealthy lifestyles, including poor diet, which lead to vascular dysfunction. And vascular dysfunction is characterized by one to several impairments, including a reduced capacity of vessels for dilation, an increased rigidity of arteries, and or a high blood pressure. And these impairments can be detected by non-invasive measurements in humans, including respectively assessments of endothelial function, arterial stiffness, and systolic and diastolic blood pressure. Vascular function and related disease can be protected by other lifestyle factors, especially physical activity and the high consumption of plant foods, which are known to protect vascular function from dysfunction. And the hypothesis that gain more and more attention is that vascular function constitute a key target of polyphenols in the mediation of their health benefits. And the research in this field is highly active. So in the second part of my talk, I will illustrate this research by focusing on some major categories of dietary polyphenol on which my group has worked. To start, what do we know about citrus flavonants and cardiovascular health? For recall, the major flavonants present in orange is asparagine, whereas the major one in grapefruit is narangenin, and both of them are present in foods as glycosidic forms, namely asparagine and narangenin, respectively. A consisting body of evidence from a number of prospective cohort studies supports the benefit of consuming flavonants for cardiovascular health. For example, a study on a US cohort has reported an inverse association between coronary heart disease and flavonon intake, with results observed for a daily flavonon intake achievable with one serving of citrus foods per day. In another cohort, the higher intake of flavonants were associated with a 20% decreased risk of stroke. Animal supplementation studies with flavonants, including some carried out in my group, have reported reduction in atherosclerosis development and an improved dilation of aortic roots. However, for a long time, clinical data and mechanistic studies were lacking. And to fill this gap, we have providing some clinical evidence of the contribution of asparagine in the beneficial effects of orange juice on vascular protection. For that, we carried out a randomized control trial in healthy, middle-aged, and overweight men, consuming daily and during 4 weeks 500 milliliters of orange juice or of a controlled isoenergetic drink supplemented with purified asparagine in the same amount as that present in orange juice, or the third drink was a control drink with a placebo in replacement of asparagine. And we have compared, after 4 weeks of intervention, the impact of the consumption of these drinks on vascular endpoints, namely on blood pressure and on endothelial function. What we have observed is that after 1 month consumption of orange juice, we observed a marked decrease of diastolic blood pressure, and this decrease was fully reproduced by the intake of pure asparagine, indicated that asparagine mimic the effects of orange juice on diastolic blood pressure. In addition, when measured postprandially at the same time, at the time point corresponding to the peak of asparagine in the plasma, both orange juice and asparagine intakes improved endothelial function. However, as you can see in the figure, the response to the juice was higher than that of asparagine group, indicated that asparagine contribute to the effect of orange juice on endothelial function, but also that other constituents present in orange juice participate in the improvement of the vascular reactivity. We carried out another clinical trial to determine if narangenin, the flavonants, the major flavonon present in grapefruit, we have so carried out another clinical trial to determine if narangenin was able to exert vascular protective effects in humans. This study was done in postmenopausal women, consuming for 6 months a third liter of grapefruit juice naturally rich in naringine, or of a controlled beverage mimicking the composition of grapefruit juice in nutrients, micronutrients, but without naringine. And we did not observe differences between the two groups regarding systolic, diastolic, or endothelial function measurements. However, we showed that the regular consumption of grapefruit juice is beneficial for arterial stiffness, and that naringine was responsible for this effect since it was not observed in the control drink without naringine. In the first clinical trial carried out with orange juice flavonants, we also carried out a microarray analysis to examine the effects of the chronic consumption of orange juice or of hesperidine on the gene expression profile of leukocytes that were isolated from the blood of volunteers sampled at the end of the intervention periods. First, we observed that 80% of the genes modulated by hesperidine were also modulated by the juice, indicated that hesperidine contribute to the genomic effects of orange juice. And the observed changes in gene expression indicate a shift toward an anti-atherogenic and anti-inflammatory profile after orange juice or hesperidine consumption. And the bioinformatic analysis of the differentially expressed genes revealed that most of the modulated genes were involved in chemotaxis, adhesion, leukocyte infiltration, and lipid transports. All these processing are at the origin of endothelial dysfunction, which is itself at the origin of atherosclerosis development. And the observed changes suggested a lower recruitment, adhesion, and infiltration of immune cells into vascular endothelium. However, the validity of this hypothesis resulting from bioinformatic analysis has to be tested and validated. And to reach this aim, we had to answer the following question. Can plasma hesperidine metabolites be able to modulate the adhesion of human monocytes to endothelial cells exposed to a pro-inflammatory environment? For that, we needed first to identify the major hesperidine metabolite present in human plasma after the intake of orange juice. This was done, and 3 main metabolites, including 2 glucuronides and 1 sulfate derivative of hesperidine, has been identified and quantified. And second, in collaboration with chemists from the University of Avignon, we have obtained purified molecules by chemical synthesis and tested the capacity of these compounds when used at the concentration nutritionally achievable. We have tested the capacity of these compounds to affect cell adhesion process in cell experiments. In brief, we have exposed human monocytes to the purified hesperidine metabolites prior to the incubation with endothelial cells, challenged with TNF-alpha, a pro-inflammatory cytokine which induced endothelial cell dysfunction. And then we have measured the impact of this exposure on the adhesion between monocytes and activated endothelial cells. As you can see here, in agreement with a nutrigenomic study on human leukocytes that have suggested a lower adhesion of circulating immune cells to the vascular endothelium, the exposure of monocytes to plasma hesperidine metabolites reduced monocyte adhesion to activated endothelial cells, and these results support the capacity of plasma flavonoid metabolites to preserve vascular endothelium and thereby to counteract the initiation of atherosclerosis development. To continue, I propose a quick focus on anthocyanins, another very important group of flavonoids, particularly abundant in berry fruits. And I will show you a few findings regarding the impact on cardiovascular health. First, epidemiological data have consistently reported about an inverse association between the higher intakes of berries and the risk of myocardial infarction. A 9 to 14 reduction in coronary heart disease has been reported when comparing higher versus lower anthocyanin intake. Over these last year, clinical studies with anthocyanin-rich products have reported improvements in biomarkers of cardiometabolic health, including improvement in endothelial function, platelet function, blood cholesterol, and insulin sensitivity. In addition, like for citrus flavonols, dietary supplementation of anthocyanins from berries have also reported that anthocyanin exert anti-atherogenic effects in animal models. And in the same supplemented mice for which anti-atherogenic effects were observed, in our group, we have also carried out a transcriptomic analysis of the aorta of these mice. And this analysis has revealed that anthocyanin modulates the expression of a high number of genes, and most of them being involved in the early steps of atherosclerosis development, including, again, monocyte adhesion and transendothelial migration. And using a mixture of plasma anthocyanin metabolites in cell experiments, we showed that the pre-exposure of activated endothelial cells with these anthocyanin metabolites present in the plasma after berries intake reduced both the adhesion of monocytes to endothelial cells as well as their transendothelial migration. Regarding now another type of polyphenolic compounds, which is particularly abundant in the turmeric spices, I will introduce some experiments that we have carried out in the lab. First, in a mice model of atherosclerosis, we showed that dietary supplementation with curcumin slowed down atherosclerosis development by reducing lipid deposit in the aortic roots and also by decreasing the infiltration of macrophage into the subendothelial space. And the transcriptomic analysis of the aortas of these animals revealed that curcumin modulates the expression of a number of genes involved in the early steps of atherosclerosis development, suggesting that the processes of cell adhesion and transendothelial migration could constitute key targets of curcumin to maintain vascular health. Based on these results, we then examine to what extent curcumin can be able to affect the adhesion of monocytes to endothelial cells and their transendothelial migration under physiological shear stress conditions, mimicking the strength exerted by the blood flow on the vascular wall in physiological conditions. For that, in an in vitro model suitable to measure transendothelial migration and using video microscopy, we measured the number of monocytes which adhere to the endothelial cells monolayer and the number of transmigrated monocytes. And that we observed is that curcumin reduced both the monocyte adhesion and transendothelial migration in conditions mimicking the blood flow in the body. To continue with mechanistic aspects, we also assess the effect of curcumin on the integrity of the vascular endothelium by measuring the impact of curcumin on the permeability of confluent endothelial cells to dextran. We showed that the permeability of TNF-alpha activated endothelial cells to dextran was reduced by 44% when curcumin is present. And the comparison of the immunostaining of actin cytoskeleton in the presence or in the absence of curcumin revealed a lower contraction of TNF-alpha activated cells when curcumin is present, indicating a better vascular integrity. And taken together, these results indicated that curcumin inhibits permeability of endothelial cells by acting on cytoskeleton organization. To end with curcumin, in a randomized controlled trial assessing the effect of an acute intake of curcumin on the modulation of endothelial function, we observed that the vascular response highly differed between the volunteers. Some subjects responded and others did not. Consequently, at the level of the whole study population, we failed to observe the significant difference between the placebo and curcumin group. And significance was only achieved in subgroup analysis. Indeed, we showed significant interaction for gender and for gender and when the cardiovascular risk score was lower. This indicates that we observed positive response of curcumin only in women and in subjects with a lower risk to develop cardiovascular disease. To conclude this talk, a brief summary of the major findings resulting from this research. First, a consistent body of clinical and mechanistic evidence support the contribution of polyphenols in the vascular protective effects of polyphenol-rich foods. Second, by acting as signal molecules, as I showed here by the modulation of gene expression, notably, dietary polyphenols can preserve vascular function and integrity by reducing the interaction between circulating immune cells and vascular endothelium, which are interactions at the origin of vascular alteration and atherosclerosis development. And the biological response to polyphenol consumption can vary between subjects, indicating that some individuals can get more benefit of polyphenol intake than others. However, the main factors of variability must be identified, and this is crucial to be able to evolve in the future toward efficient personalized nutrition to prevent disease using polyphenols. Just before ending, I'd like to briefly introduce my research group at INRAE. The NutriVasc team belongs to the Human Nutrition Unit of Clermont-Ferrand. And as introduced by Emmanuel at the beginning of my talk, the research aim of my team is to assess the role of plant food bioactive in the prevention of vascular-related disease. And to this end, the research includes different aspects: the characterization of the complexity of the exposure of the human body to plant food bioactive by the food metabolome approach using untargeted metabolomics. I have not talked about that, but this is also an important part of the research in my group. And we also work on the development of online database containing detailed information about food phytochemicals and their human metabolics, and this database is called PhytoHub. We also worked, and I have show you some results of this aspect. We are working on the in vivo demonstration of the vascular protective effects of plant food bioactive and the identification of their mechanism of action using combining targeted and nutritionist approach. And we are also working at the better understanding of the individual variation of the response to their intake, and we are working on the identification of the determinants involved. if you are interested in this kind of research, of course, you can contact me. And off to end, I'd like to thank all my colleagues and students in my group that have contributed to the research presented today. Thank you very much for your attention.
Thank you. Thank you very much, Christine, for your very comprehensive and interesting talk. So I'm sure that the young chemists that were looking for the molecules will find a lot of complementarities and purposes for the molecules they are isolating, that they are working with. Okay, so we are waiting for questions from the audience. So I hope that we can have some from the young chemists. Probably meanwhile, so we can I can just start just with a question or a challenge to you, because our problem, we are the food chemists, is always when we have these isolated molecules and we can see this effect, and as you showed, sometimes when we go to the food, there are some other molecules that are also relevant for explaining the effect, sometimes maximizing the effect, sometimes minimizing the effect. So you show that with the asparagine and the orange juice, for example. So we, as we need to do, is always looking for the highest content of molecules, so the molecules that exist in higher amounts. But this small amount of other molecules, what are the role? Do you think we can really isolate the compounds and use them, for example, as food supplements, or should we use these molecules integrated in the food?
So that is very, thank you very much for the question, Manuel. What is very important to know is that the native compounds found in foods are now those recovered in the body after absorption and metabolism. So this is very important because for many years, a lot of in vitro studies have used raw extract on cell experiments and have reported about effects that are not observed in vivo because the native molecules are not those that are acting in vivo after absorption. So it is important to know that these compounds are intensively metabolized, and that the active compounds in the circulation are conjugative derivatives or compounds, smaller compounds of microbial origin. So it is very important to keep in mind the bioavailability and the metabolism of these compounds when we want to study the health effects. And it is important. Your second question was, do we have to isolate the compound?
Should we have food supplements because we are isolating the compounds and we are increasing this amount in the superfoods, or should we use the foods as they are with the natural ingredients?
Yes, what is recommended, clearly recommended, is not to go to supplement, but to eat as much as possible a diversity of foods, plant foods that are individually rich in a variety of plant food bioactives, including polyphenols and other one. And that is very important, is to as diversity as large as possible of the intake of these different compounds to optimize their benefits. But if we use supplements, we ingest a high amount of a special type of compounds, and maybe we don't know, but if we know that these compounds have beneficial effects at very low concentration because they act as signal molecules, mainly in the body, and if we increase too much their bioavailability, we can have some side effects, and we have no mastering of that. So we may be aware of models for example, which are known to improve microparticles and so on, which are known to increase a lot the bioavailability. It is not necessarily the best thing to increase a lot the bioavailability, because we know that these compounds are benefit when they are present at low concentration because they act as signal molecules, but we don't know what can happen if we have too much delivery of these compounds in the body. Maybe we can have side effects. We have some example of that, but the physiological effect is good at low concentration, and it becomes deleterious at high concentration in vitro studies. So we have to be very careful with that.
Okay, thank you. I don't know if we have questions from the audience or from the internet. I'm asking the organization if there are some questions that I'm missing. No, so I received information that there are no other questions. Of course, we could keep talking about all these molecules and the interactions that these molecules have with the different cells that we have, the different receptors, but unfortunately we don't have time. So, my last word to you, Christina, is that I hope you can also be in contact with this Portuguese community of young scientists in chemistry, because I think your work and in where you are, so can have much to provide to our young chemists.
Yes, that's why I have introduced the last slide to present another activity which is more on metabolomics aspects, because this is particularly interesting for chemists, and we have already welcomed Portuguese young chemists in our lab to work on metabolomics and the databases aspect. That's why I have added this slide at the end. So. Okay. They can contact us if interested in the future.
Yes, thank you very much, Dr.
Thank you very much to you.
Thank you. See you.
Thank you.
Okay, so we are now moving for the second talk of this session, this Friday session. So, and it's really my pleasure to introduce you, Dr. Daniel Granato, that I am not sure if he is in Finland, but the affiliation is the Natural Resources Institute in Finland. But as you can see by the name, so that cannot be denied that Daniel Granato is from Brazil. So he speaks Portuguese and he is my friend. Okay, so it's my pleasure just to introduce Daniel Granato. That is a food engineer and got a PhD in food science. So currently he works as an associate professor at the Natural Resources Institute in Finland. And these research projects are related with food science and the technology. That's why one of the reasons why he is here in this session of food and technology. And so he works on chemometrics and process product optimization. So he is associated editor in several journals, such as Food Chemistry, Journal of Food Science, Current Opinion in Food Science, PLOS ONE, Molecules, Data in Brief, and Foods. So, of course, Sandy, his work is well known for all of us that work in food chemistry. So, and it is really my pleasure to hear the talk of Daniel Granato related to recent analytical trends in food authenticity based on chemical markers. So, Daniel, the floor is the virtual floor is yours.
Yes, thanks a lot for the introduction. Good afternoon, everyone. Actually, it's good morning in Portugal, right? Right now here in Finland, it's already almost 1. So good afternoon, and thanks a lot for the invitation. It's always good to be in Portugal, even though it's virtually, but I'm really happy to be contributing and talk about these issues with you. I think the COVID pandemics have created like lots of space to debate food. And I don't know about Portugal, but in Brazil and also in Finland, we have quite many kind of scandals. And we have, at least here in Finland, we have a huge protection for the local foods. But the competition is quite high because we have different prices, we have different products from many different places. And can I actually say that one product is coming from a certain country, or if the product is organic, or if it's biodynamic, or etc. So we are moving forward in a way that we are going very keen into the analytics, into the chemistry, and try to look for markers to try to distinguish and to differentiate products. And so I'm coming here to show you a little bit of the work we've been doing, and also people from all over the world. We are trying to look for solutions because fraudsters, they are getting more and more sophisticated. And we in food science and technology and chemistry overall, we need to be better. We need to find ways to detect what they're doing actually. So I'm going to talk about frauds in foods and beverages, some analytical arsenal to detect the fraud, some gaps and trends in food authenticity, and we're going to make some concludes, and I'm going to make some questions to all of you. So when we think about food authenticity or even food fraud, if only in Science Direct, you can see by the numbers. So it started like in 1998 with 100 papers, and then 10 years later we had like almost 300, and then 10 years later we had like almost 800, and so on. So we have quite many papers dealing with food fraud because it seems to be working at some point. It might be profitable even, because most of the fraudulent or the fraudsters, they are looking for money. Obviously they want money, but in many of the cases they just want to mislead the consumer. But can we trust them? The food producers, we have to. They need to abide by the law, considering all the aspects of food production. But I'm gonna ask you guys that. How do you actually trust what's written on the label? Do you trust 100% in all products that you see on the shelves? Or you have like some doubts and say, hey, does it really come from a very tiny place in Sweden or something like that? So we are eager to understand why it happens. And my special focus is on the ways to detect the fraud, considering, of course, the chemical aspects, the chemical markers of these foods. So when we think about food fraud, we are talking about substitution of ingredients. We are talking about contaminants as well. We have gray markets everywhere, from China to Brazil, going through Japan and everywhere. We have tampering, we have mislabeling, we have unapproved enhancements, overruns, counterfeiting, dilution, and so on. It's quite easy to make any fraud in the food chain, because if we think about all the unit operations during the food production, it's quite easy to understand that it's super easy to do that. But of course, we don't want that. And most of the producers, they abide by the law, but we still see many cases of frauds. So these are some of the questions that when you go to the supermarket, you might be facing. So are the labels correct? I mean, are the labels trustworthy? So is this bread really made with highest grade flour? Is the chicken from a free range or not? Is that real cheese? So these are only very simple questions that we can pose. And as scientists, we need to always have some doubts until somebody proves you wrong. So when we think about some of the trend news, the hot news about honey, for instance. So food companies are under tremendous pressure. So you have the honey, but you don't know if it's where it comes from and if that is actually honey. So this is one of the most expensive type of foods, but we have many others like herbs and so on, meat. So my question to you is, how safe are we if we consider all the food chain and we are talking about dilution, tampering, counterfeiting, chemical compounds that are added into foods that might be very toxic, just as the case of melamine in milk? And is food authenticity a matter of public concern? What do you guys think? Okay, you're chemists. I am a food engineer. So aren't we in the middle of something that we have the chemistry, the food science and technology, and the public health all in the same level, like with the hands, giving hands and say, hey, we need to work together. I do think we are partially safe, but we always need to have both eyes very open, right? And it is food authenticity. It is a matter of public concern. And obviously, you all know that when we think about foods, we have a cheese, we have beverages, we have different extracts, we have meat, oils, and so on. They are very complex samples. We have thousands and thousands of compounds. But is there like any compound that we can actually take it and say that, well, this is the marker of the authenticity, or this is the marker to differentiate different types of products? And we can easily do that nowadays. So we have to think about some stuff. Why the food authenticity is so important? Because I don't know about you guys, but I'm gonna tell you my case. When I go to the supermarket, I usually get one cheese that I really like from one brand because I know how they work, or I've been there, or if I haven't been there, I know that they have certification for that, for making that cheese, for instance. So I trust the company. So this way of trusting and respecting traditions are super. I know in Portugal, for instance, I just bought like some hours ago vinho verde, like the green wine. So it's delicious. It's dark. So I'm kind of respecting the tradition, and I do like it. I trust the vinho verde. So when we think about Finland, for instance, we have a thing for our strawberries. Our strawberries are delicious. You cannot imagine it. They are super delicious. So we are proud to say it's made in Finland. And we have this brand. It's this registered brand, Tehty Suomessa. So it's made in Finland. So this is something that we respect and we trust when we have something like this on the label. And what about when we go to Italy and then we try to get a prosciutto, presunto? So it's really obvious that if I am selling just like this product, and my product it's not coming from Italy, or my strawberry is not coming from Finland, and I'm putting on the label that it is from Finland or from Italy or elsewhere, I'm going to be a fraudster. So we do need to respect the traditions. We need to have quality control measures to verify that what people are producing is actually okay. They are complying, they are abiding with the law. So we need to talk about product identity. So there are ways, there are chemical analysis that can be done to actually identify the any counterfeit in these products. So I'm gonna show you this example. So obviously these are just examples. I'm not saying which is authentic or not, but only looking at the labels, which one is the authentic one, and how trustworthy can a label be? Have you guys thought about it? So just looking at the label, oh, this is golden clear. Oh, this is from a local beekeeper. Is it? How can we trust? So is there a way, chemically speaking, to differentiate these products? Oh, just by the color. Really? Can't I counterfeit the color? I do, I can. So we need to have chemical markers that can be able to differentiate all this. Okay, so can we build a model to classify the objects and then detect the fraud with, let's say, 95% of confidence? Yes, right now we do have all the ways to do that. So I'm going to show you some of these methods. Okay, and obviously interesting to get to know which will be the parameter used to characterize these objects. Is it like in the case of the honey, can we quantify a mineral or a phenolic compounds or a sugar? Yeah, so there are many ways to tackle that. Okay, so when we think about chemometrics, or we think about food fraud, actually we have the chemistry, and then we generate a bunch of data, a large data set containing thousands and thousands of data, and then we have the chemometrics, which is like a set of statistics and mathematical models and procedures that we can use to identify compounds and also to discriminate what is what. So these are really interesting, and when we talk about food authenticity or food fraud, we need to use such an approach. Otherwise, we're not going to see any difference. Okay, so there are some papers in the literature. I'm just going to leave some of them here. This one published by my friend José Câmara from the University of Madeira in Portugal. The current trends and the recent advances on food authenticity technologies and chemometric approaches. There are many others. Authenticity and traceability of in beverages to combat food fraud, a gap analysis. So if you see, these are all published in food chemistry journals, but if you dig in, there are like many others published in different journals, just more into analytical chemistry or organic chemistry and so on. So when we talk about the food authentication, there are basically 4 different types of approach that we can use to detect and to actually quantify the adulteration in foods. We have chromatography, such as gas chromatography, liquid chromatography, and then we have the spectroscopy, which is much easier to deal with because most of the techniques are non-destructive. So we have infrared, we have FTIR, Raman, NIR, MIR, SIRS, NMR, and so on. And the mass spectrometry is also something really interesting in a way, because we have very high resolution and we can have the time of flight, and then we can detect with very, I mean, very accurately which type of compound, and also the quantity. And nowadays we can also use electronic sensors to help in this differentiation. And of course, we have many others. I'm going to show you some of these examples in the literature. I could be speaking here like for ages, because this is a topic that I love. And I'm just going to show you here my ex-supervisor, Professor Van Ruth from the Wageningen University. She wrote many different papers, and I really recommend you to take a look at them, because they are really interesting in many ways. So the food frauds and the vulnerability assessments, the food fraud and the key factors. So we have many different ways of looking at food fraud and food authenticity. And here, when we have the opportunity related to, and then we have the risk factors and the motivations related to food fraud. And then if we think about all the control that the industry and also the government can actually do in those companies, and then we have what we call the fraud vulnerability. So we need to have this quality control from the government and from the industry, looking at everything that is being produced in a country. Okay, so this is also something interesting. But then a question: how can I make, or how can I propose quality control measures if we think about chemistry? Obviously, we can use different analytical methods and data analysis ways to look at this. Okay, so I'm going to show you some of the examples about these analytical methods used to detect fraud in food and beverages. So we have the commodities here. We have chocolate, we have coffee, rum, we have whiskey, olive oil, honey, and so many others. So these are quite the most frauded products that we see, because they are quite easy to be done, and we see quite a lot because they are purchased every day, everywhere. Just one example, we have this brand, the Johnny Walker, and we have products ranging from 16 euro to up to 200, 300 euros, depending on the country and on the taxes. But this is a quite different price, right? And in all these products, we have a different percentage of malt. The aging process is different. We have different types of barrel. The geographical origin also might be changed. If it's reserve or if it's not reserve, everything will impact on the price. So obviously, this product is really reliable. But if I want to make my own company and I am a fraudster, so I want to say, oh, this is from the best malt. This is aged for 30 euros, and actually it's not. I just added, some compounds that give the flavor of aged barrel. So we can do like whatever. And I think the fraudsters are really, really elegant, because it's really interesting to detect the type of frauds that they have done, actually. So this is just going to show you some of the examples about fraud in the beverage and food. So here in 2018, this group published a paper on a novel approach to assess the quality and authenticity of Scotch whiskey based on gas chromatography coupled to high-resolution mass spectrometry. Really interesting in a way. So gas chromatography also coupled with carbon isotope ratio mass spectrometry to detect to detect any fraudulent. And what they have done, look, they found the markers of authentic Scotch whiskey, in different brands, so that they know they were real, they were not fake. So now we have a method to detect any fraudulent activity in whiskey. And let's say whiskey is quite expensive. And then we think about coffee. We drink it every day, most likely everywhere in the world. We have a huge amount of production every year, and Brazil is the largest producer of coffee in the world. But we have two different regions that produce this coffee, Minas Gerais and Paraná. So there are two different states. And if you look at the prices, they're almost double. But is it justified? Or Minas Gerais, which is the largest producer in Brazil, is taking advantage of the fame, of the glories to produce the best coffee in Brazil. So we decided to take a look at that some years ago, my master's student, and then we used proton transfer reaction mass spectrometry coupled to NIR, and then we tried to make a preliminary study for the use of chemometrics, and we found out we were able to classify the coffee coming from different places in Brazil, and that was really interesting. And when we look at the number of organic samples and conventional samples as well, we were able to check the most important volatiles to differentiate organic and non-organic. So, and this is in 1 minute, you have these results. Okay, so this is a way that we try to tackle the authenticity of those products. But we can do that with many other products, just like these ones. We were trying to differentiate 6 types of Camellia sinensis teas based on phenolic composition, alkaloids, and amino acids. And that's what we did. We were able to differentiate using chemometrics, using the flavonols and the alkaloids, the origin of the Camellia sinensis teas based on the chemical composition, using the alkaloids and phenolic compounds, and also the amino acids. So that was really nice in a way. Some years ago, we also tried the same approach with juices, using the antioxidant activity and the phenolic composition, using different chemometric approaches, in this case, the partially squared discriminant analysis and the soft independent modeling of class analogy, so SINCA. We were able to differentiate juices coming from different fruits using chemometrics, and also using just like some fake ones that we faked in the lab. So these are some of the other examples that I would give you about food authenticity. And here they were trying to use rapid evaporative ionization mass spectrometry to detect fraud in meat. So they were able to differentiate 3 types of meats coming from different places using this new mass spectrometry-based approach. And when we think about the analytical ways, I'm going to show you some of other examples that can be used. So this paper published some years ago is a really nice reference to describe the modern analytical methods for detection of food fraud and adulteration in different foods. If you see here, for oils, fats, fruit juices, coffee, teas, alcoholic beverages, spices, sweeteners, all this PCR, HPLC, infrared, ELISA, mass spectrometry, liquid chromatography, biosensors, Raman, NMR, and so on. So this is a very interesting paper that you guys could take a look at. And we also can take a look from the compositional data. So we're talking about major chemical compounds, even to molecular analysis. So in this case, some years ago, this group was trying to detect adulteration in Nebbiolo-based Italian wines through machine learning. There is, of course, the coupling of NMR and ICP-MS to detect fraud as well. We can access the origin of different French wines using isotope and elemental analysis, always with chemometrics, machine learning. So we have to go beyond the borders. We cannot just analyze fat or oil or something like that. And this is published last year. I thought that was really interesting. So it's a direct non-invasive molecular analysis of a packaging label to assist wine bottle authentication. So that was really interesting approach that these authors did. And of course, we can use NMR for authentication of honey, beer, and spices, and so many others. But not all companies have NMR. Not all companies have all this analytical arsenal, right? So there are many things that we should consider when we are talking about food authenticity. Okay, so these are just some of the examples I told you. And I'm going to give you some gaps and maybe some thoughts just as of some final slides. This is what we want in practice. We want the best analytical method to detect fraud, to detect and possibly to quantify the fraud. So we need to have efficient and accurate data analysis because we're going to have a huge amount of data coming from fraud foods or beverages that we can do like in the laboratory, and we have the authentic ones. So we have these two sets, and then our aim is to differentiate those sets using data analysis. So we can create and standardize protocols to make it not happen. And this can be used both by the industry, both by the industry and government bodies. So my proposition would be that for the analytical methods, both food companies and we scientists need to look at, but we definitely need money coming from the industry as well to partially cover the expenses of PhD students, master students, and different researchers. And then when we talk about accurate and efficient data analysis, obviously we are also talking about the industry trying to help us to develop this. And why is that? Why the industry should be partially paying for that? Because we are talking about not only the European Union, but different countries. So governmental bodies can use this data and all these results, because we are trying to give back to the society all the salary that we have, but all the knowledge that we have collected through the years. But the governments should also give money, more money to us, not to be rich. No, it's just to try to develop things further, and also to help the industry to control better the production. So it's a one way out. We need to have collaboration in all aspects. So otherwise, we're not gonna close the loop in the food authenticity, and we always gonna have fraud. So with that, I also would like to say that we have tackled the chemometrics in food authentication and effects of processing, and I hope I haven't spoken too much. So thank you very much for the opportunity, and please ask me questions. I would like to keep on talking like for ages, but I know I am almost 1 minute late already.
Okay, Daniel, thank you very much. So as Daniel challenges, so we have now time for questions. I would like just to invite you just to make some questions. Do you want, everybody wants to start? If not, of course, we can keep talking with Danielle, so I can have some questions.
And if somebody wants to speak Portuguese, I can help the translation, no problem.
Okay, that's mine. Based on what Danielle just said, I want also to challenge Danielle when you say that it is a consumer concern, the food fraud and authenticity. I think for us as scientists, we should avoid that it is a consumer concern, because the consumer should trust the industries, the consumer should trust the authorities. So I think this food fraud should be a concern for the authorities, should be a concern for the food industry. Of course, what are the food industry doing is that the food industry are asking the suppliers, just prove me that your product that you are providing us is authentic. And of course, sometimes the producers do not have the tools that you showed, that for them just to provide that, okay, I'm producing really, that is really health and it's
authentic.
Good. Can you comment on that?
Yes, of course. But I have to remind you, Manuel, that I come from a country, well, my dad comes from Italy, where people say there is mafia. Mafia is like fraudulent and stuff. And Brazilians made it perfect. So I come from two countries, basically, in which fraudulent activities are quite high. So obviously we have to trust, but I see in many cases that even some governmental bodies are being manipulated by industry, by industrial interests. So that's why I always have to keep two eyes open, as I said, because these things happen. And I have seen many different fraudulent activities in many other countries, even here in EU. So in the Netherlands, I have a friend who was working with spices, and we saw many different types of adulterations. So, and that's the Netherlands. So that's why we have to also consider the consumers, because if we trust everyone, I think at the end we are going to be the one losing. So,
of course, but trusting the authorities, you agree with me? Trusting the authorities.
Yes, we have to. We have to. Yes.
Yes, and we should we as scientists, we should collaborate with the authorities. So in Europe, EFSA.
EFSA, European Food Safety Authority. Yes.
Yes, so we need to trust, and I think the European countries follow what are the recommendations from the European Food Safety Authority. Here in Portugal, the ASAI is the branch of the European Food Safety Agency. So this is probably we need to collaborate more, because I cannot see that the small industries can have these tools just to do this type of analysis, but a government institution, a governmental institution could have and should have this type of instruments. And there are two aspects. That are food, the frauds can be economic fraud. So that is not a problem for our health, it's a problem for the taxes. But other frauds are really health frauds. So, but so this is only a comment, but because now we have a question, so and I would like to pass to the question. Don't comment my question, but because I want you to comment this. As consumers, what can we do to protect ourselves from this? So this is a question from Katia Santos that is saying also, thanks for the interesting presentation. In your opinion, would it be possible in the future to have quick, generalized and practical methodologies to detect fraud in food industry?
Well, let me show you that this the future is already now, I would say. There are already some applications that you can use using your cell phone, and you will scan, okay, and this will be coupled to your cell phone, and you're gonna see that if that salmon, for instance, is really fresh or not, or if that coffee is actually if there is any counterfeit. So I think overall, very soon we're gonna have these applications available here in the EU, but as a consumer now, I think we should look for companies that have certifications, like the coffee, like the cocoa, and so on. So I think this is one way to start with, because if we like in Brazil, they sell like different types of products like in the streets, and you don't know where they come from. So this is not trustworthy, you know. So I think this is one way to tackle that. Thanks for the question.
Okay, so we have here another question from Luisa Almeida that congratulates you for the presentation, and she asks, what are the major challenges to start this fraud analysis and also to guarantee the authenticity of the food?
Well, I can say that here in the European Union and also in some South American countries and most likely in Asia, you have a governmental body that issues the authenticity of the food based on documentations and based on many other aspects of the production. So if you have that in mind, and you also have contact that is direct linked to the food safety authority in each country or in each partner, you can collect original and authentic samples. And then in the lab, for instance, you can adulterate with the most common adulterants, like coffee. Coffee, they use lots of grits. So we have corn grits. There is like wheat, straw as well. And then you can put into different concentrations. Into juices, you can put different, you can even produce in the lab the authentic juices and add syrups, and then you can add sucrose, water, and so on. So there are many ways to produce all these fake foods, and the authentic foods is quite easy to be done depending on the type of foods that you were talking about.
Okay, thank you. I don't know if we have some more questions. If not, so let me do another question that is
yes.
related now. So we talk about, so fraud is always improving. So imagine, and we need to think always what can be the next step. So imagine that there is some people that can, so if you define what are the markers, okay, so good idea. So can I add this marker to my product in order to disguise this and okay, now it is authentic.
Yes, I really doubt that this will be the case, because I think not even Sigma Aldrich have all the standards for, you know, for analytical purposes, not even to give in such a depth. So I think that fraudulent activities will not go to that direction, because it's not chemically viable. But if it was, I'm sure it would into that direction, but I don't think that's the case.
Okay, so it was just a question, just that. Okay, so imagination, that always we need to have imagination when we are talking with
Yes.
scientists. Okay, so
Yes.
Daniel, so we are approaching our time. So we have now the coffee breakers and the poster sessions. So Daniel, thank you very much. It was my pleasure to see you. So we met in China, we met in Spain, now we met virtually in Portugal. I hope we can meet personally one of these days here in Portugal. Thank you very much, Daniel, for your...
Muito obrigado. Thank you very much, Maria Diaz and also Manuel, for the collaboration. And thanks a lot for the invitation. It was amazing.
Thank you, Danielle. Your talk was amazing. Thank you so much for enlightening us for this subject that is very impacting in our lives as a consumers, and it was great. Thank you so much, and thank you, Dr.
Thank you
for your excellent talk. It's great to hear from you, and thank you, Professor Manuel Coimbra, for chairing this session. And as you were saying, let's begin now the coffee break and the poster session. So don't forget to vote on the 3 best posters, and see you again at 11:30. If you want to, Professor Manuel and Dr. Danielle, if you want to stay in the Zoom meeting, you can stay in the Zoom meeting so you can actively participate in the next session. So see you soon. See you in half an hour.
See you soon. Obrigado. Tchau, tchau.
Bye-bye.
Tchau, Manuel. Até.
Bye-bye.
Hello again. Good morning to you all. Welcome to the second session of today's work. So without further ado, I will pass on to Professor Dr. Mario Berberan Santos, that will be the chair of today's session. Thank you so much and enjoy the Congress.
So good morning to everybody. I hope many participants will still join us. It is my pleasure to introduce all speakers, and particularly I will start with Professor Elena Ibanez. Hello, Elena.
Hello. Hi.
Hi. So it is my pleasure to introduce Elena, and she works at the Institute of Food Science Research of the Consejo Superior de Investigaciones Científicas in Madrid. She received her PhD in analytical chemistry at the Universidad Autónoma de Madrid and had postdoctoral positions at Brigham Young University and the University of California at Davis, USA. Professor Elena's main activities include the study and development of new green extraction techniques and processes based on the use of compressed fluids to isolate bioactive compounds. She has received many national and international awards, co-authored more than 230 publications, 29 book chapters, and 10 patents. In 2016, she was one of the top 50 women in analytical chemistry. Professor Elena, pleasure. You have the floor now. Please proceed.
Okay. Well, thank you, Mario, and thank you, Maria, thank you, Mario, for the introduction, and thanks, Maria, and the organizing committee of the Portuguese Young Chemist meeting for inviting me. We had to wait for 1 year, but finally we are here. And I hope all of you are doing fine, and I hope soon we will be able to meet each other and have even more interaction, to give talks in front of the computer, and not be able to see the people in the just in front of you is quite difficult. Well, not difficult, but it's not as interesting as being in life. But anyway, today I want to put in the floor this question, and I will try during my presentation to answer, or at least to give you my answer about this: how can green Photonics change your life? I mean, I will be introducing what the Photonics concept is, and also the green Photonics, and I will show you like a case study that we were developing here in the laboratory. So as Mario told you, I belong to the Scientific Council, or in the Spanish Council of Scientific Research, in the Institute of Food Science Research, TIAL, in Madrid, and in the Laboratory of Photonics. And this work has been done also in collaboration with the Universidad Nacional de Colombia. So the first thing I want to, if it works, let me see. Okay. Well, so yeah. So we are talking about so great challenges that we are facing today and towards the 2030, that are the achievement of trying to achieve the Sustainable Development Goals. And among them, we are focusing the zero hunger, and that means the end of hunger. But this is related also to food security and improved nutrition and promoting a sustainable agriculture. So in order to reach this goal, we have to focus in the new approaches on the agricultural development, and we have to work really hard in terms of food security and nutrition, but also to allow an easier access to safe and nutritious food for sustaining life and promoting the good health. And in this framework of the Sustainable Development Goals and this work or this pushing towards sustainability, in the area of food analysis, we have been trying to implement some principles related to the green chemistry and also green analytical chemistry principles. But as you can see in this figure, that is, well, it looks like it looks quite difficult, but anyway, I want, well, difficult to explain. At least I won't explain every arrow that is in this pyramid. But what I want to show you here is the link that we have found between the green analytical chemistry principles, the application of these green analytical chemistry principles, and the green chemistry principles to obtain or to reach these sustainable development goals. So, for instance, in green analytical chemistry principles, you have it in here. So there are many, but if we can at least, well, we can choose one of them. Like, for example, these select direct analytical techniques that, if you can see here, it links to the increase of energy efficiency in terms of green chemistry principles. And then this can somehow, I mean, following these two principles, we can improve sustainable development goals like the affordable and clean energy. We can also work towards the industry, innovation, and infrastructure, and also in terms of sustainable cities and communities and a climate action. So we can do this with all the different principles. So my main message in here is that by making an effort and trying to apply these principles in our daily life, in our food, in terms of food analysis, so we can push towards the achievement of.
Elena, excuse me,
sure.
you're not seeing your screen.
You are not seeing my screen, and nobody is seeing the screen?
I received messages about
it.
No, we cannot see it.
Oh, come on. So let me, oh, sorry. So apologies. Wait. Okay. Now?
Yeah, okay, now it's perfect.
Okay, so, okay, apologies. So, okay. Now let me, I have to take you to, so. Okay. But okay, so well, I start, well, not starting over, but so I was talking about the Sustainable Development Goals and these new approaches needed for this agricultural development for food security and nutrition, allowing an easier access to safe and nutritious foods, for sustaining the life and promoting good health. Now, I hope you can see this pyramid here. So in which, in terms of food analysis, we are placing these green analytical chemistry principles and green chemistry principles, and how both following these principles, we can help promoting these sustainable development goals. And I was putting an example, and I will put another one since nobody has seen the screen. Apologies for this. So, for example, I will choose this one in this green analytical chemistry principles, is the generate as little waste as possible and treat it properly. So by using this, this principle is connected also in preventing waste in the green chemistry principles. And this can, if we follow these two principles, we can improve also sustainable development goals as the clean water and sanitation, the sustainable cities and communities, and also climate action, life below water, and life on land. Okay, so this is just to, well, it's quite, I'm not going to explain all of them, but it's just for you to realize that in our day life, in this, when applying this food analysis, and using this, making the effort of using these principles, the green chemistry and green analytical chemistry, we are pushing and helping towards the sustainability. Okay. So green analytical chemistry methodologies can be applied in terms in food analysis in different areas. For instance, we can work on the selection of foods or ingredients, and in terms of availability. And how can we do that? So it's using these clean technologies in terms of, for instance, biorefineries, and in order to push also to the circular bio-based economy. But also we can apply these green analytical methodologies for determining the food safety and quality of the food safety and quality in order to determine if the products that we are obtaining are safe to consume, and also to evaluate the individual nutritional status. Okay, and this way we can reach, as I was mentioning, this food security and zero hunger achievement. So I was talking about the green Photonics, and first I want to define what is Photonics. That was defined for the first time in an SCI journal in our group as a discipline that studies the food and nutrition domains through the application of advanced omic technologies to improve consumer well-being, health, and confidence. So, but as I was mentioning, this talk is about green Photonics. That means applying this green analytical chemistry and green chemistry principles in this Photonics process. So in this sense, we can recognize the application of these principles to the development of green processes to obtain, for instance, food ingredients that can be used in providing new type of foods, or even foods that can be used to prevent certain diseases. And we are doing this mainly in applying this biorefinery concept. That means that we are going to use trying to make use of all the biomass that we have in front. I mean, when you will see it with an example, but it's when we have a biomass, we try to obtain and to split this biomass in different type of products that can be later on employed, for instance, in the food industry, but not in the food, also only in the food industry, but also in the cosmetic industry and other applications. But the goal is a zero waste. I mean that everything that is in this biomass is later on applied, okay? So, and this can be done using green processes. But also in this Photonics, we can apply these green analytical chemistry principles in the different parts of the omics platform, mainly in the transcriptomics, proteomics, and metabolomics that we are applying to evaluate the food safety, food quality, food traceability, and food bioactivity. This is the typical workflow that we are using in the Photonics lab in the development of new functional ingredients. So we start always using our different sources, like, for example, natural sources like plants, but also they can be food byproducts, wastes, algae, microalgae. Okay, so this is our biomass, yes, our starting point. We develop these green extraction processes. The extract that we obtain, we characterize using advanced analytical techniques. We carry out in vitro assays, in vivo assays, or sometimes clinical trials. We select the extracts with the highest bioactivity. And these extracts, for example, we treat cells, and we obtain RNA, proteins, metabolites, fractions from control and treated individuals. That can be, as you will see in the example, cells, colon cancer cells. And with these fractions, we carry out this Photonics evaluation, in which we analyze the transcriptomics, proteomics, and metabolomics. So this Photonics evaluation, after a data processing and a statistical analysis, we carry out these biomarkers, or this is our final goal, try to identify biomarkers, confirm that they are in our product, but also to identify the pathway or the molecular mechanisms that are associated to a biological activity that we have previously seen in vitro or in vivo assays. Okay. So this is the example that I'm going to show you is this application of the green Photonics in food byproducts and wastes. So everybody knows that the food byproducts and waste is now it's one of the problems that we are facing, and actually this is one also of the goals in the sustainable development goals, that is number 12, is trying to reduce these food byproducts and waste, because, well, numbers are really important, because we have to consider that about 1/3 of the food produced globally is lost or waste along the food supply chain, from the primary production up to consumption. This waste depends on the different countries and distribution of in the countries, but as in general, this is the number. It's about 1/3 of the food produced globally. That means it's about 1.3 billion tons of food byproducts and waste are generated annually. And if we go a little bit deeper, we can realize that from these byproducts, 1.3 billion, it's about around 15% are generated from fruit and vegetable production. Okay, and one of so we have these byproducts or these wastes, and so we have different ways of trying to reduce these food byproducts and waste. Of course, we can reuse them or recycle them, but there is another possibility that is a valorization. It's develop a valorization strategy in order to produce some bioactive compounds that we know that are present in these food byproducts and waste, in order to improve the economies of the different places or the different communities that have this food byproduct. Okay, so this is important, not only from the point of view of obtaining bioactive compounds that can help preventing certain diseases, but also because developing these valorization strategies, what we are doing is reducing the environmental impact of this food waste or food byproducts. So this also, well, it goes more towards the sustainability because it allows us to reach other sustainable development goals. Okay. So in our laboratory, what we have done during many years is trying to develop this biorefinery based on the use of green processing technologies. So in this case, we have there are different processing technologies as compressed fluid extraction, microwave assisted extraction, high pressure and temperature reaction, biotechnological processes. But among all of them, we have quite important background in the development of compressed fluids extraction processes. So even if they can be these products, they can be valorized as fuels. So we are, as I was mentioning, mainly focused in obtaining these high added value products that are part of these food byproducts and waste. So this can be used as a bioactive compounds, as a drugs, or can be also biopolymers. So the workflow you can see here. So we have this food byproduct, we extract, we characterize the presence of these high added value products, and we carry out this Photonics evaluation. So this is the work that the work that I'm going to present you is a work that was carried out by in the PhD dissertation of Diego Ballesteros, that was the PhD student from the Universidad Nacional de Colombia. Okay, so his project was based in the fruit byproducts valorization, and there were tropical fruit byproducts because, well, there were important byproducts that were obtained in Colombia. So among them, you could see here, well, some well-known, like for instance, mango. Okay, so and from mango we try to valorize this seed kernel. Also, we have the Uchuva physalis that we valorize the calyx. So this film that surrounds the fruit. And also we have this Curuba, Passiflora mollissima, in which we valorize the seeds. Okay, or we try to valorize the seeds. So in his dissertation, we developed this also this workflow. So we carry out the pressurized liquid extraction of the fruit byproducts. Okay. In some cases, this pressurized liquid extraction, the factors that we were optimizing, and also the solvents that we were employing, were based on this study of solubility of the target bioactive compounds that we know that were present in the fruit. For instance, in the case of the mango, we knew that mangiferina, that was the main bioactive compound that was had been already defined and identified by other authors as potent, for instance, anti-proliferative agent against different type of cancers. Okay, so that was the first step, this extraction, and then we quantify the target compounds, carry out the chemical characterization, and also some other in vitro assays like total phenolic content, total flavonoid content, and antioxidant activity. With all this information, we select the extracts, okay? And the selected extracts were used for in Diego's PhD to determine their anti-proliferative activity against T29 line cell. This is a colon cancer cell, okay? And we select the most bioactive extracts to carry out, in this case, a metabolomics and transcriptomics study for the final photomics evaluation, okay? With the main idea was to start from the beginning with the biomass, and then to be able to demonstrate and to be able to determine which was the molecular mechanism behind the action of this of the different extracts that we evaluated. As I was mentioning, the example will be based in this Passiflora mollissima Bailey seeds. Why it's important? So it's because, well, in this case, the residue on or the waste is really big. It's about 30% of the whole fruit, and it's called a passion fruit. Okay, this passion fruit is a fruta de la pasión. I don't know how it's called in Portugal, but we in Spain we call it. We knew it by this name. Okay. So and the seeds, okay, are, as I'm mentioning, about 30% of the fruit. Okay, here you have a picture. And with these seeds, we run this flow. First, we carry out this sequential pressurized liquid extraction for lipids and phenolic metabolites. We select the solvent for the first step, which is the defatting process of these seeds. We optimize by using a response surface methodology. For the second step, we carry out the chemical characterization, antiproliferative activity of the optimal extract, again, this colon cancer HT29 and normal colon cells, and these metabolomics and transcriptomic studies. Okay, so if we go to the first step, what we did is we knew that the content of the fat in the seeds was quite important, so we decided to carry out this sequential extraction. In the first step, we remove the fat that can be also used. That can have different uses. And for this first step, we evaluated the use of different solvents. So we evaluated the method. This is the chloroform methanol. This is a blight and dyer method that is employed for many analytical scientists for determining the fat content of a product. So this could be like the control base. It is about so with this information, we knew that the fat content of the seeds was about 7.3%. Okay, and we evaluate the use of different solvents. Among them, hexane, that was the mainly used in most of the conventional processes. So our idea was to try to remove or to avoid the use of N-hexane, and that's why we tried different solvents that, even if they you can think that they are not safe or they are toxic solvents. I can tell you that these are for instance, cyclohexane or heptane. They are proposed as a substitute of hexane in terms of they are safer and they are less toxic. Okay, so we evaluate the use of, as I mentioned, in cyclohexane and heptane, and also limonene as a bio-based solvent. So, but as you can see here, not always the bio-based solvents are the ones that provide the best results. So in this case, we run this kinetics for the extraction yield using the different solvents, well, we can, for instance, select the cyclohexane as a substitute of hexane with very similar results that were achieved in a very fast way. Okay, in PLE, but with 10 minutes and with using a lower amount of solvent, we were able to obtain very good results. Okay, so once the seeds are defatted, we have the biomass that can be extracted for a polar fraction. Okay, but in this case, since the fraction of this passiflora seeds was not described before, so we have no targeted compounds to go for in this valorization strategy. So we didn't apply it in this case the Hansen solubility parameters, but we use different. So a more general strategy that uses as independent factors in PLE, in pressurized liquid extraction, the solvent composition and the temperature. Okay, solvent composition, we select ethyl acetate, ethanol, and the mixtures. Okay, and temperatures from 50 to 150. We run this central composite design, and the responses we select were the extraction yield, the total phenolic content, the total flavonoid content, and antioxidant activity. Okay, so this is these are the response surfaces that we obtain for this optimization. We have it for the extraction yield, for the total phenolic compounds, the flavonoids, and the EC50 and TEAC. These are values determining the antioxidant activity of the extracts. Okay, so well, most of them you will see that have the maximum at around 100% ethanol and the highest temperature. You will see here. Okay, and finally, when we optimize this multiple response, so this is what we obtained, that for all the variables, for all the response variables, the optimal conditions were 100% ethanol and 150 degrees centigrade. Okay, these are the predicted responses by the model, and these were the values, the experimental values obtained. So you could see that there is a close correlation among them. So if you remember the workflow, now the extracts that was, so under these conditions, the extract obtained at 100% ethanol and 150 degrees was chemically characterized. And in this case, so this was the non-polar fraction that contained all the fatty acids and squalene, for example, and sterols that are part of this of the fat extracts from the seeds. Okay, so with this information, we can know the composition of the fat in order to determine if it's good for being introduced in a different oil, or if it can be used alone. Okay, and also from the second extract, the one obtained to extract the polar fraction. So we analyze, well, the other one was analyzed by using GC with coupled with a QTOF, that is a high resolution mass spectrometry. And for the polar fraction, so we determine this using liquid chromatography with QTOF also. So this is the chromatographic profile, and we could identify many compounds, among them phenolic acids, proanthocyanidins, and different type of flavonoids. Okay. So the selected extract was also tested in terms of its antiproliferative effect on this cancer cell lines. Okay, this is and these are normal colon cancer, colon cells. Okay, and these are treated at different concentrations. Okay, and we determine this the effective concentration and the selectivity index. So you could see here that after so with these 50 micrograms per milliliter, we had a clear difference between among the viability, the action of these extracts against this HT29, just compared to the normal cells. Okay. So after this, so we treated these cells. So here, so we took this and this, the treated cells in both cases, okay, untreated and treated cells. So and we ran this metabolomic study, okay. So we use this the cells treated with the colon cancer, okay, and also this with this culture medium. We made these different replicates and we extract the metabolites. So this is the workflow for extracting the metabolites, and we determine we acquire the data, processing and analysis. This is and also we determine this this metabolomics profile, and carry out this principal component analysis in which we could see that this well, there are some there's some difference between the control and the treated cells with this passiflora. And with this information and using this variable importance in projection scores, so we could see which were the metabolites that were able to discriminate between the control and treated cells. So we also ran this transcriptomic study on the same cells, okay. So, and this is the workflow, the RNA extraction and sample preparation and data acquisition and processing. And what we determined was that the cells, the treated cells, the effect of the extracts in the treated cells was able to activate somehow 500, more than 500 genes in the treated cells. Among them, we had downregulated 257 and 249 were upregulated. So, so finally, we saw this. We studied which were the transcription factors that were activated and inhibited, and we identified them. Okay, which were the most important. So this way, we were able to realize which were the main mechanisms that were affected by the addition of this extract in the media, in the cells. So that means that, for instance, the resistance to stress, the unfolded protein response, and the cyclin-dependent kinase inhibitor were inhibited. That means that, for instance, if we focus on this resistance to stress, that means that the cells, the mechanisms was against, so they decrease this resistance to stress, and therefore they were more prone to die or to be less viable. Okay. In terms of activated, the transcriptional mechanisms, so for instance, it was the cell proliferation and DNA break repairs. Okay. So, so with this, well, this is only to show you which are the possibilities given by this integrated strategy, in which we put together some theoretical tools, compressed fluid extraction, in vitro assays, chemical analysis, and also with towards a sustainable valorization in this case of tropical fruit byproducts, as a source of bioactive compounds, phenolic acids, flavonoids, and proanthocyanidins, in trying to develop an ingredient able to reduce or decrease the speed of proliferation of these HT29 colon cancer cell lines. Okay, and with this Photonics study, we knew that this extract was able to focus in the cell cycle regulation by antioxidant response modulation and on DNA replication. Okay, so my final conclusion is that I think I'm going good. I'm going right on time. The final conclusion that I want to tell you is that the green Photonics allows the developing sustainable processes based on green chemistry and the use of compressed fluids, aim at the extraction of compounds with biological activity from different natural sources. And as I was mentioning, these processes, they can be used as sample preparation techniques also that can be used, that can be employed in the different analytical protocols that we use for Photonics studies. So when implementing green Photonics together with green analytical chemistry and green chemistry principles in our daily work in food analysis, we are working towards sustainability. And my last message to take home message is that it is not only our duty as scientists, but also our opportunity to give a future to the coming generations. And with this and the picture of our research group in a year, every year barbecue that we have once a year so just for enjoying food and friendship. So with this picture, I want to thank all the group, and I want to also to thank you for the invitation and for being with me in this presentation. Thanks.
Thank you very much for your excellent and timely presentation. We have time for a few questions.
So, I don't see how. Okay, how to see you? So,
well, you can stop sharing if you want.
Oh yes, I stop share. Oh, okay. Okay.
So, any questions? Well, if not, I have a few for you. Well, first of all, I think the translation of passion fruit is maracujá. It's not exactly the same, but it's very similar. So in our case, it comes from a word from Brazil.
So you've been working with this with maracujá, I guess. So
no, I'm just saying it's the Portuguese.
Okay.
Okay, so one question is about the extraction solvent you used. Can you tell us what is the position of supercritical CO2?
Okay, so supercritical CO2 is one of my favorite. I mean, the people that know that knows me, so it's one of my favorite solvents. In this case, I mean, it has many advantages. Okay, so why didn't we use this as a first step for the defatting? Because supercritical CO2 is mainly used when used alone, is mainly used for the lipid fraction. Okay, so and in this case we didn't use it because we wanted to develop a sequential process using the same system. It's an integrated process in which we use the same equipment for a sequential extraction. So in this case, we were not able to combine supercritical food extraction in the first step and pressurized liquid extraction in the second step. We did this many times, mainly for developing these biorefinery processes, but not in this case. Supercritical fraction usually gives lower extraction yield, okay, but the extracts are more concentrated in the compounds of interest, and also it allows not to prevent the thermal hydraulic. Well, it prevents to lose the bioactive compound. So it has many advantages, and we use it a lot, but not in this particular case. Yeah.
Okay, thank you. Any other questions? Well, if not, we should proceed. Thank you very much again.
Okay, thank you. It has been a pleasure. Okay.
So, Angela, please go ahead.
So, good morning, everyone. First of all, I would like to thank the organizing committee for the invitation to be present at this panel of presentations. It is a great pleasure to be part of such a prestigious congress and with such renowned researchers. So let's move on to oral communications. I am pleased to introduce Ana Rita Circuncisão. Ana Rita is from Universidade de Aveiro and will present a work entitled Photonics of brown microalgae, Laminaria digitata and Emmentalia elongata, from structural evidence to bioactive effects. So Ana Rita, when you're ready, you can proceed with your presentation. Thank you.
Okay, good morning, everyone. So I will share my screen. So are you seeing my presentation?
Yes.
Okay, so just put this here. Okay, so good morning, everyone. I'm Ana. I'm a PhD student from University of Aveiro, and for this presentation, I will show you some results within the FCT project AlgaFlor concerning two fluorotannins from brown macroalgae Laminaria digitata and Emmentalia elongata from structural evidence to bioactive effects. So nowadays, the world population is increasingly aware of the impact that nutrition has on health. And for this reason, people have started changing their eating habits, searching for more healthy and natural food products. So in this sense, marine macroalgae appears one of these healthy food alternatives, being already included in the list of superfoods due to their richness in key nutrients and bioactive compounds. Macroalgae can be divided into green, brown, and red ones. And between them, brown phylum is in fact recognized for its abundance in key macronutrients and exclusive phenolic bioactive compounds that are closely associated to important biological activities. So one of these compounds are fluorotannins that are exclusive phenolics from brown algae. They belong to the tannins family and are composed by fluoroglucinol units that, depending on the number of hydroxyl groups and on the type of linkages, can originate different fluorotannins. So their type and molecular weight can greatly vary between algae species and with seasonality. And of course, as phenolics, fluorotannins are closely associated, exert different biological properties, namely antioxidant, anti-inflammatory, and anti-diabetic. Although, and besides their health benefits, the direct consumption of macroalgae as food ingredient in Europe is still incipient comparing to Asiatic countries. And for this reason, several efforts have been made in order to try to incorporate them as ingredient in food products. However, this incorporation faces huge challenges since the strong odor and taste of seaweeds often limits the percentage of macroalgae that can be used and impairs some sensory and biological features of the new formulated food products. So a trend strategy to try to overcome these problems is the use of macroalgae, crude extracts or purified fractions. And in fact, due to its biological potential, biofluorettanins are being prospected as a potential functional food ingredient. Although in this field, there are some questions that need to be addressed. For example, what about fluorettanins bioaccessibility? Are they really bioactive after digestion, and how may their structure influence its bioactivity? So we tried to answer some of these questions, and the main objective of this work was in fact to evaluate the influence of in vitro digestion on the bioaccessibility and potential antioxidant and anti-inflammatory activity of crude and purified fluorettanins-rich extracts from two edible European brown macroalgae, namely Laminaria and Ementhalia. So for the extraction of fluorettanins, each macroalgae was purchased as a dried powder and submitted to a conventional solid liquid extraction using 70% acetone, thus allowing to obtain a crude extract. So this one was then submitted to solvent partitioning using firstly N-hexane and then ethyl acetate to extract the fluorettanins and obtaining at the final an aqueous residue. So both extract and partition fractions were characterized quantitatively by the spectrophotometric, the MBA assay, and also qualitatively by the UHPLC-IMS. So based on the results from the MBA and the chromatograms, we selected the crude extract and the fluorettanins-rich extract from each algae to be digested. So all extracts were firstly freeze-dried and were characterized in terms of their content of fluorettanins by the MBA and also in terms of their biological properties. And then the extracts were submitted to in vitro digestion, which includes an oral phase, a gastric, and the intestinal phase. So in each phase, we collected liquids that were analyzed in terms of their content of fluorettanins and in terms of their biological properties in order to understand the effect of digestion in the bioaccessibility of fluorettanins and what happens to their bioactivity. So here I show you the results respecting to the extraction yield for each algae of crude and the partitioned fractions and also their respective fluorettanins content that is expressed on the graphs. So we can see that the extraction yield of ethyl acetate, the fluorettanins-rich extract, is in fact higher in Laminaria comparing to Ementhalia. And we can see, and this is in accordance with the graphs above, from which we can see for both algae that the acetate fraction was the richest in fluorettanins content, followed by the crude, the hexane, and the aqueous fraction. Also, in more detail, we saw that the fluorettanins content in the crude from Laminaria was 4 times higher than the crude from Ementhalia, and the acetate, the fluorettanins-rich extract, was 2 times higher than the acetate from Ementhalia. So, based on the fluorettanins content, we decided only to inject the richest fractions. And here I show you the total ion chromatograms of the acetate fractions for both algae. And we can see immediately that the chromatogram for Laminaria is quite more defined than the Ementhalia, probably due to the higher content of fluorettanins in Laminaria. Also, we see clearly over retention time in both chromatograms that, and specifically between 10 and 24 minutes, a mountain-like effect that is characteristic from samples that contain this type of compounds. In fact, once fluorettanins are polymeric compounds, the UHPLC column doesn't have capacity to separate them. And this is one of the biggest challenges when we are working with this type of polymeric compounds. However, these chromatograms allow us to understand and allow us to verify that at 10 minutes, they are eluted fluorotanins with lower degree of polymerization, and after that a mountain is formed by the fluorotanins with higher degree of polymerization. Also, the chromatograms allow us to identify some double charge ions that allow us to estimate that the laminaria may contain fluorotanins with lower degree of polymerization at 20, whereas Imathalia may contain fluorotanins with higher degree at 30 fluoroglucinol units. So in order to see more details about fluorotannin structure, we selected for acetate for the fluorotanins rich extract some mass ranges characteristic from low molecular weight fluorotanins with degrees of polymerization between 3 and 8, and this way to see the data allow us immediately to verify that in fact laminaria may contain or seems to contain fluorotanins with a lower degree of polymerization than Imathalia, which of course may influence its biological properties. So here I show you the influence of the 3 stages of the digestion process in the content of fluorotanins for both algae, of the crude that is represented at white, and of the fluorotanins rich extract here in green and here in blue. And the first impression is that the content of fluorotanins decreases for all extracts, decreases along the digestion process. Also, the calculations show that the bioaccessibility percentage of crude in laminaria was 58% and 71% in the acetate, in the fluorotanins rich extract, contrasting to the lower bioaccessibility percentages obtained for Imathalia. So all these may us to suggest that fluorotanins content seems to be affected by digestion, mainly in gastric phase, probably due to the acid conditions, and also fluorotanins from laminaria seems to be more resistant, stable to digestion in comparison to fluorotanins from Imathalia. So regarding the biological properties, both the crude and fluorotanins rich extract from laminaria showed higher radical scavenging capacities than Imathalia, and being the acetate fraction in both algae the most prominent. This difference between the scavenging capacities can be explained taking into account that laminaria may contain fluorotanins with lower degree of polymerization, which has been linked, according to the literature, to greater biological properties. So when submitted to digestion, all extracts show a decreased scavenging capacity along digestion, particularly from gastric to intestinal phases. However, the acetate, the fluorotanins rich extract from laminaria at intestinal phase preserved about 57% and 66% of the initial scavenging capacity, although the acetate fractions from Imathalia have lost practically all the scavenging capacity, as well as the crude extracts. So all this may has to suggest that the structure, the type of fluorotanins present in each type of algae may affect their biological properties, being the fluorotanins bioactivity critically influenced by its bioaccessibility. So in conclusion, we verify that laminaria has a higher content of fluorotanins with lower degree of polymerization compared to Imathalia elongata. And from the in vitro digestion process, we see that more than 50% of the fluorotanins from purified fraction of laminaria are in fact available to be absorbed, and This preserve more than 50% of the initial radical scavenging capacity. So doing this work allow us to understand that the selection of the brown algae as a source of the Phlorotannins functional ingredients is in fact an important step in the development of functional added value foods. So as an ongoing work, we are currently doing tandem mass spectrometry to try to understand what type of families of Phlorotannins are present in laminaria or in Menthalia, and also to support his work, it will be very important to perform bioavailability studies using Calco2 cells. So thank you for your attention.
Thank you very much, Ana Rita, for your excellent work and communication. Let's check if there are some questions in YouTube chat. So far, no. Let me ask you something.
Okay.
So, especially in the case of Emmentalia elongata, there is a significant decrease in the bioaccessibility of Phlorotannins between the oral and the intestinal tract, correct? I would like to ask you if is how these algae are consumed and whether the possible effects of different processing or pre-treatment methods have already been considered by your group to increase the bioaccessibility of the Phlorotannins.
Okay. So, in fact, there is a decrease of Phlorotannins between from oral to the intestinal phase that is more prominent in Emmentalia. In fact, Emmentalia is composed by, or it seems that is composed by a higher degree of polymerization Phlorotannins, and it seems that they are how can I say it, are more susceptible to the digestion process. Maybe we can purchase the Emmentalia elongata as a dried powder, and maybe we can, for example, do another pre-treatment to try to conserve the Phlorotannins. But in fact, we are based on these two algae. We are focusing, in fact, in the laminaria and not in Emmentalia. Okay. But we are performing another alternative methodologies, for example, microwave, to understand if using another methodology can increase the content of Phlorotannins in Emmentalia. And when we do, when we submitted the extract from Emmentalia from microwave that have a higher content of Phlorotannins, the percentage of the bioaccessibility percentage can be higher. Yeah, okay. This is ongoing work.
Okay, thank you. There are no questions so far. I think we may proceed.
Okay, thank you.
Thank you very much, Ana Rita. So now we will proceed with Fernanda Machado. Fernanda also belongs to Universidade de Aveiro and will present a work entitled Influence of Processing Parameters on Coffee Compounds Hypoceramic Potential. So Fernanda, when you're ready, the floor is yours. You may start your presentation.
So, hello everyone. I'm going to share the screen. Tell me if you can see it. Ready?
Yes.
Okay. Okay, so good morning everyone. My name is Fernanda Machado and I'm a PhD student. And I would like to thank you for the opportunity of being here today. And I'm going to talk to you about the influence of processing parameters on coffee compounds hypocholesterolemic potential. So cholesterol is an essential molecule of our body. It modulates membrane structure and function. It can act as precursor of bile acids, vitamin D, and essential hormones. However, if cholesterol is present in excess, it can accumulate in our arteries, causing a condition called Arterosclerosis, increasing the risk of the development of cardiovascular diseases. So cholesterol is synthesized in the liver. And here I present some of the steps for its synthesis. And since cholesterol is a very hydrophobic molecule, it needs to be first solubilized, emulsified, in order to be absorbed. And this emulsification is done by the action of biosalts, which are actually originated from cholesterol. And these biosalts are then conjugated with glycine or taurine, which confers them a more amphiphilic nature. So after major meals, our gallbladder will secrete these biosalts to our intestinal lumen, and they will form micelles on the cholesterol coming from the liver and the diet. It will emulsify them and then carry them to the brush borders of our intestinal lumen. And then cholesterol can be absorbed. So to avoid developing the cardiovascular diseases, there are several hypocholesterolemic strategies. They can act on decreasing the synthesis of cholesterol. They can decrease its absorption or increase its excretion. So we have pharmaceutical strategies and functional food that can act on decreasing cholesterol. On the pharmaceutical ones, we have statins, which will decrease the endogenous synthesis of cholesterol. We have ezetimibe, which will decrease its absorption. We also have resins, which will sequester biosalts and will contribute to increase the excretion of cholesterol. In the functional food, we have phytosterols, which will compete with cholesterol for its absorption. We have polyunsaturated fatty acids and soluble fibers. However, these strategies are costly. They have reduced efficiency and selectivity. They can present severe side effects, mostly in the case of the pharmaceutical ones. They are based on hydrophobic matrices, which can be a technological challenge, and their intake time is not after major meals, which would be the optimal time to affect cholesterol absorption and solubility. So there's a need for more effective food ingredients that have a proper intake time to maximize their effectiveness, and there's a need for a wider range of food ingredients hydrophilic. So the goal is to find a food product or matrix that can fulfill all these characteristics. So we have coffee that has an intrinsic nutrient richness. Its content can be modulated. It's usually taken after major meals. It's part of people's daily habits, and it's a hydrophilic matrix. So in a previous work, we've studied the in vitro hypocholesterolemic effect of coffee compounds, namely its polysaccharides. And we saw that in the presence of different coffee extracts, we have a solubility decrease of cholesterol. So we can add here that coffee can have a hypocholesterolemic effect. So based on this previous work, we now wanted to study the influence of coffee processing parameters on coffee compounds' hypocholesterolemic potential. So we have all these factors that could affect coffee chemical composition. And in this work, we maintained the origin, the species, the blending, and the brewing method, and we varied the roasting degree and the level of grinding. So we wanted to see if by modulating these two factors, we could change or affect coffee polysaccharide content and its structure, and see if this would consequently affect their hypocholesterolemic properties. So we started with an Arabica Brazil coffee provided by Feb Cafés. And then we industrially roasted it using two different roasting degrees, the light one and a dark one. Then we grinded these beans using two different levels, the level 1, which was we obtained a finer particle, and level 3, in which we obtained a coarser one. After that, we brewed these coffees using a typical espresso coffee machine, and we obtained our coffees. After that, we freeze-dried our coffee brews and did some ethanolic precipitations to selectively precipitate our polysaccharides. So we started with a dialysis to separate the high molecular weight material in which these polysaccharides are present. Then we did the centrifugation and obtained a residue and a soluble material. And from the soluble material, we did our first ethanolic precipitation at 50% ethanol. And then we centrifuged and obtained our first precipitate, the ET50 fraction. From the supernatant, we then did our second ethanolic precipitation at 75 ethanol. and obtained our second precipitate, the ET75 fraction. So these fractions were analyzed regarding their sugar content using gas chromatography. And in the first precipitate, the ET50 fraction, we can see that's mostly rich in mannose residues and galactose, which is the typical profile from coffee galactomannan. We can see here in the backbone is mainly rich in mannose residues. And in the side chains, we have galactose. So looking for the ratio of mannose galactose residues, we can see that with an increase of the roasting degree, we have an increase of this ratio too. Since this ratio is related with the branching degree of this polysaccharide, we can say that by increasing the roasting degree, we can obtain an increase in the ratio of mannose galactose and then obtaining a less branched galactomannans. Regarding the other precipitate, the ET75 fraction, we can see that's mainly rich in galactose, mannose, and arabinose residues, which is typical also from the arabinogalactans from coffee. And here in the main backbone, we can see galactose, and in the side chains, it's composed mainly by galactose and arabinose residues. So looking for the arabinose residues, we can see that it decreased with the increase of roasting because this residue is very labile. And then we can say that by increasing the roasting degrees, we obtain less arabinose residues, which could indicate that the size of this arabinogalactan side chain is decreased. So after that, we wanted to evaluate the effect of the different coffee roastings on cholesterol solubility. So for that, we used an in vitro intestinal model composed of glycodeoxycholic acid, which is one of the most representative biosalts present in our intestinal lumen, and we used cholesterol labeled in carbon 13 and followed these molecules using carbon 13 quantitative NMR. So in the spectrum, we can see in green, we have the biosalt. And then when we add cholesterol, we have the appearance of, in black, of this peak at 44 ppm. The other colors is related with the coffee light roast and dark roast. And we can see that when we add these coffees, there's a decrease of cholesterol. After the quantitative analysis, we can see that the light roasted coffee had a higher effect in decreasing cholesterol when compared with the dark roasted one. We also compared with the resin, cholesterol, which is a pharmaceutical strategy used to decrease cholesterol. And we can see that coffee is still a bit far from this effect, but still it shows promising results. After that, we went to test the different fractions that we isolated with the ethanolic precipitations. And we can see that the ET75 fraction, the one rich in arabinogalactans, had a better effect in decreasing cholesterol when compared with the galactomannan-rich fraction. We also did some experiments enriching the light roasted coffee with these fractions, and we can see that the coffee enriched with the arabinogalactan fraction had a better effect in decreasing cholesterol. So concluding, we saw that different roasting degrees can affect hypocholesterolemic properties of coffee. Namely, the light roasted coffee had a better effect than the dark roasted one. We also saw that the hypocholesterolemic effect observed for coffee when enriched with the arabinogalactans fraction was higher when compared with the coffee enriched with galactomannans. Also, we saw that coffee brew had showed to affect cholesterol bioaccessibility in a larger extent than the fractions alone, which could indicate that coffee could have other compounds with hypocholesterolemic potential, aside from these polysaccharides. As future work, we want to complete the set of these cholesterol bioaccessibility assays, namely the different grinding levels, because the ones that I presented were regarding the finer particles. So we want to do the other ones with the coarser. And we also would like to extract and characterize other compounds present in coffee with hypocholesterolemic potential, such as melanogens and lipids, and also to evaluate the effect of gastrointestinal digestion fermentation on coffee brews and extracts and see how this process can affect cholesterol bioaccessibility. So thank you for your attention, and thank you again for the opportunity to be here today.
Thank you, Fernanda, for your excellent presentation. Let's check if there are some questions. So far, there aren't any. Fernanda, let me ask you an additional point of your future investigation. Are in vivo work planned to validate these effects, the effects of these polysaccharides on cholesterol absorption?
If we have in vivo?
In vivo, yes.
It's still a long way to go, I think. But yeah, for now, we're going to do this in vitro studies. Still want to test the toxicity and the bioaccessibility in the cacao cells, and then do these studies in the digestion and the fermentation and see how it will affect. And then after that, we'll move on to maybe the in vivo studies.
Because it's a very promising result that you have in your work. So,
thank you.
Congratulations. There are no further questions. So let's move on to the next presentation. Thank you, Fernanda.
Thank you.
We will then proceed to the last communication of this panel. I am pleased to present Miquel Añibarro Ortega. Miquel is from CIMO, Instituto Politécnico de Bragança, and will present a work entitled Development of Bioactive Purple-Red Colorants from Red Raspberry Waste using heat and ultrasound-assisted extractions coupled with RSM. So, Miquel, the floor is yours. When you are ready, you can proceed with your presentation.
Thank you, Angela. Can you hear me?
Yes.
Okay. Can you see the presentation?
Yes.
Okay. So, hello everyone. I'm Miquel Añibarro from Centro de Investigación y Montaña in Bragança. I'm going to present this work about the development of bioactive purple-red colorants from red raspberry waste using heat and ultrasound-assisted extraction coupled with response surface methodology. Colorants have been widely used in the food industry to improve and change the color of fruit products, and while controversial artificial colorants have been widely used, their natural counterparts have been less selected due to the limited availability, higher cost, and stability issues. Within this kind of additives, the anthocyanins are naturally occurring pigments. They are commonly found in berries, and they are water soluble. As you can see in this picture, they present attractive colors, and they also present health promoting effects. So the main objective of this work was to develop a novel anthocyanin-rich food colorant from red raspberry waste. And for this, we did the characterization of the anthocyanin profile of the raspberry using heat-assisted extraction and ultrasound-assisted extraction. Then we optimized those extractions using the statistical tool of central composite design coupled to a response surface methodology. And finally, we evaluated the colorant and the bioactive properties of the extract obtained under optimal conditions. So, first of all, from the freeze-dried powderized red raspberry, we did a heat-assisted extraction. This was carried out in a thermostatic bath using hermetic glass vials, and the ultrasound-assisted extraction was carried out in a focused ultrasound system using a titanium probe. The used solvents were water ethanol mixtures acidified to pH 3 with citric acid. So from the hydroethanolic extract, the ethanol and the water was removed in order to obtain the dry weight. and the dry extract were ready solved to inject them into an HPLC system. So from here, we obtained two different variables or response. One of them was the anthocyanin content, and the other one was the extraction yield or extracted solids. So the liquid chromatography allowed us identifying and quantifying two anthocyanins, concretely two cyanidin glycosides. And in order to maximize the previously mentioned responses, we built a 5-level central composite design with 6 central points, 6 start points, and 8 cubic points. And we studied the time, the temperature, and the solvent in the case of the heat-assisted extraction, and the time, the power, and the solvent in the case of the ultrasound-assisted extraction. We also built a response surface in order to graphically observe the optimal conditions. So this led to a total of 40 experiments, 20 extraction for its extraction method, and we observed the responses extraction yield, individual anthocyanin content, and total anthocyanin content. These results were fitted into a polynomial equation model after the statistical validation based on a non-significant lack of fit and a high determination coefficient. Here we can see some of the response surfaces. For the case of the heat-assisted extraction, the extraction yield was promoted by high temperatures, and the anthocyanin content was promoted by long extraction times. In the case of the ultrasound-assisted extraction, the extraction yield was promoted by medium power values, and the anthocyanin content was promoted by short extraction times. Here we can see the optimal conditions for each response variable, and also considering all the response variables together. And we can observe that the heat-assisted extraction achieves a slightly higher extraction yield and total anthocyanin content than the ones obtained with ultrasound-assisted extraction. However, in the case of the ultrasound-assisted extraction, it required much less extraction time. So this could be a more sustainable process. We also checked the predictive capacity of the model. It was experimentally validated. After obtaining the extract under optimal conditions, we evaluated some bioactivities. For example, for the evaluation of the antioxidant activity, we measured the capacity of the extract to inhibit the lipidic peroxidation and the oxidative hemolysis. We also checked the antimicrobial activity of the extract using the microdilution method against several bacteria, and some of them were foodborne bacteria. And we also measured the color of the extract using optical colorimetry. So regarding the antioxidant activity, here we can see the effective concentration of both extracts, and we can observe that the extract obtained by heat presents a slightly higher antioxidant activity than the other one, and this could be due to its higher content in anthocyanins. Regarding the antimicrobial activity, here we can see the minimum inhibitory concentrations of both extracts, and we can observe that they present antimicrobial effect against Escherichia coli, Morganella morgani, Pseudomonas aeruginosa, Enterococcus fecalis, and Listeria monocytogenes. And concretely, in the case of Morganella and Pseudomonas, both extracts present even better effect, antimicrobial effect, than the ampicillin used as positive control. Regarding the color, we can see that both extracts have practically the same color, and they don't differ too much from the original lyophilized powder. So To conclude, we can say that the raspberry has a very high content in cyanidin glycoside. The heat-assisted extraction yielded a slightly higher anthocyanin content than the ultrasound-assisted extraction, but this seems to be more sustainable because it required less extraction time. And both extracts show antioxidant activity and antimicrobial effects, especially against Morganella morgani and Pseudomonas aeruginosa. And with all that, we can say that the raspberry waste seems to be a good option as a source of bioactive purple-red colorants. For the future, it will be interesting to study the stability of the developed natural colorant and their incorporation into real food matrices. If you want to see more detailed information about the work, you can check this paper. It's open access in the platform MDPI and the journal processes. And I would like to thank to my group, Centro de Investigación de Montaña and IPB. I'm really happy to work here and feel really lucky to work here. Also to the organization committee to giving me the opportunity to present this work, and the FCT for my PhD grant, and all the involved institutions. And also thank to you for your attention, and enjoy the rest of the Congress, and take care of yourselves. Thank you so much.
Thank you, Mikel, for your great presentation. Let's see if there are any questions. No, but let me ask you something, Mikel. Your study aimed at the optimization of extraction methods for the development of natural food colorants, correct?
Mm-hmm.
However, why did you also evaluate the bioactive properties of the red raspberry extracts?
Okay, so the principal objective of this work was to obtain a natural colorant, but anthocyanins, they are known to be very bioactive, as Professor Christine says before. They are polyphenols, so they are known to be really bioactive, and that's why we evaluated the antimicrobial and antioxidant properties, because these properties are directly related to the preservative capacity of the compounds. So we can say that the developed colorants also could present a preservative effect for the food products.
Okay, that's a great work you are developing. So thank you, Mikel. For now, the communications are finished. Mario?
Yes, this is the end of the session. I thank again all our speakers for their excellent contributions. And that's the end of the session. Thank you.
Thank you so much. Thank you for all your communicators that gave us the opportunity to get to know about their work that they are doing right now. So thank you again for the chairs, also Dr. Marino Barberan and Angela Liberal. Thank you so much for your insights about the oral communications, and also to Dr. Elena Ibanez for her wonderful presentation. With nothing less to say, let's finish here the morning session. We will meet again this afternoon at 2:30. Thank you so much and see you soon. Bye.
Thank you.